talk about like the slide says that I talk on cryptography, right? But cryptography are not light topics actually. They are like really important topics. Like many of the times in history, it happened that some king's life was dependent on the cryptography they used. Many of the times, some war was lost because the cryptography was broken by the enemies, and so it's pretty important thing for communication. But I'll be like talking about like how like the most of the important cryptographies that we saw in history. So let's say, what is cryptography? So cryptography is, for example, Anna wants to send some message to Oscar, and she wants to do that in some way that only Oscar can understand the information that Anna is sending. And if I try to like see the message in the meantime, and I shouldn't be able to like see what Anna is saying to Oscar. Okay, that is cryptography, like sending some information to the intended person, but make sure that nobody else other than these two persons understands this. Okay, so what they have to do is like they have to meet at some point, and they have to like think about some information that these two persons shares, and then with that shared information, they can like make sense of the message that he receives from Anna, or Anna receives from Oscar. But anybody who doesn't have the shared information, they won't necessarily be able to understand what's going on within this. So this picture basically says that what goes in usual cryptography. You have some plain text. This is the shared information, and then you do something in the plain text using this shared information, and then you generate the ciphertext, and then Anna sends it to Oscar, and Oscar gets the ciphertext, and using the shared information that in the world only Anna and Oscar knows, Oscar is able to decipher the ciphertext. Okay, so let's see first of the very primitive ciphertext we saw in history. So this is called Caesar cipher. So what happens is, for example, Anna wants to send hello to Oscar, and they said that okay, N is gonna be the key. So this is the information they both share, and nobody else knows. Now, by key, Anna is meaning that whatever you see in my text, A is gonna be N. Okay, and B will be O, and C will be P, D will be Q, E will be R, so on and so forth. Okay, so in Caesar cipher, the text that Anna is trying to send to Oscar, hello, becomes this. Any question? Is it like understandable? Yeah. Okay. So imagine you have one book, okay, and you take out all the spaces and punctuations, right? And then you, using some sort of key, you encrypt the whole book. Is it like, will you be able to read the book after the encryption? What do you think? There will be no spaces, there will be no semicolons. Everything other than these texts, other than the 26 characters, will be omitted. So how would it look like? Just a mess, right? So Caesar discovered it maybe more than 2,000 years ago. And after 1,000 years, people were baffled, okay, we cannot break this thing. You take all the punctuations and spaces and you just cipher using this thing, and nobody can read it. After 1,000 years, it's around 1,000 something. People knew how to break this thing. So what would be your idea? How would you break this thing? If you receive for example, Kevin, you receive something like a huge text that Anna is trying to send to Oscar, and you have it. What do you do? crying is not an option. Yeah. You wanted to say something, Craig?
Getting all the
Getting all the doubles?
yeah.
And then?
Comparing to like, for example, like there, y, and then you compare some doubles that we have and then
So what Kevin is saying that in English we know that okay, L, like many of the words that has like double L. So if you see something repeated, it probably says that it's L, right? Kind of something. So yeah, you're like to that point, but the thing is, the key to deciphering the Caesar cipher is something like this. So in the standard English, you see all the text, and if you see the distribution, you'll find that A appears 8% of the time. Okay? And E comes 12% of the time. So this is kind of the distribution that English language has. Maybe in Spanish, it's something different. Maybe in some other language, it's something different. But if you know that Anna is speaking English to Oscar, then and you have like this distribution, it can help you, right? So if you take a look at the previous slide, that these two L's become one, right? Now, what happens is, what Kevin does, Kevin receives a huge, the large amount of text that Anna was trying to send to Oscar, and he makes a distribution like this, and he sees that okay, Y appears at the same amount of time as E appears. What does it say? Y is actually E, right? So it was basically discovered by Muslim scientists, where like they had the Quran, right? So they thought that there must be something like miraculous inside it, and they like started looking at occurrence of different characters that is found in Quran, and then they suddenly discovered these things. So after thousands of years, there was a major breakthrough that okay, now we know how to like break the Caesar cipher. No matter which key you use for Caesar cipher, E will always stand out like this. If you have a large amount of text, you'll see that some of the characters will be like big one. Okay, so in the history there was always battle between the code makers and code breakers. Code makers was trying to like make something that nobody could understand. And code breakers would like come up with something like this and break the privacy between Anna and Oscar. So after that one, like code breakers had the victory, like yeah, we got it. And then code makers had to come up with something to secure, like to make the connection between these two guys again. So what happened next? This happened. So the French cryptanalyst, he came up with a cipher that is called Wigner cipher. I'm not quite sure how to pronounce it, but let's say like Wigner cipher. So he said, okay, so in Caesar cipher, the size of the key is what? Just one, right? Just n. But Wigner, he supposed that, okay, so let's make a bigger size of key. For example, in this case, the key is 5 words, lucky. So how does it work? First time, so for example, we want to encrypt hello using lucky. So the first character we want to encrypt, we go to the first heap, and we see H is S. Right? The next one, I want to encipher E. What is going to be E? I go here, E is Y. So can anybody help me? Like, what would be lucky? Hello in cipher? S.
Y.
Y.
H. N.
N.
N again.
L.
and Z.
No.
And Z.
N.
N.
What happens to the second L?
Z.
Oh.
B or? You guys understand how it works?
Yeah.
Yeah, Z, right?
Yeah.
B.
Yeah, it's the.
B, like violet, B.
The violet, uh-huh.
Okay. And then what happens to O?
No, it's actually W.
Oh, don't worry, just what happens to O? So here, right? Okay, boom. So look, previously the L was like repeated, right? In case of the Caesar cipher, what happened to this L was Y twice. But in case of the Wigner cipher, what happens? Is like N, L becomes once N, next time it becomes V, right? So what happens is, for example, Jonathan is coming like in a disguise so that nobody can know who is he. But I know he's tall, like the E has a big bar right here. So no matter how hard he tries using the Caesar cipher, I'll always know that there's tall guy, handsome guy is Jonathan because he is like this tall. Now, as soon as he starts using the Wigner cipher, he gives his height to somebody else. Like he's like maybe 6 feet. Now he gives like 1 feet to, I don't know, Anna. And now he comes to the room and nobody knows who he is, right? So Wigner cipher, or this is called like Lecimbre indecipherable. That means in plain is the cipher that cannot be broken, basically. So because the code breakers, they came up with the frequency analysis, right? Now what he does is like if E repeats like a couple of times, E becomes one time maybe O, the next time the same E becomes P or something. Now you cannot just apply the usual frequency analysis to see like you would understand that. Okay, so clear up to this point? Okay, good. Now that was a victory for the code makers. Yeah, we got it. Like nobody can break our codes and stuff. And then many centuries nobody was able to like break this cipher. Once Anna and Oscar they like come up with like a common word like okay, now lucky girl will be our password. Nobody was able to break what they're trying to convey. Now what happens is after a couple of centuries, during the time of Charles Babbage, Babbage was like challenged by one of the guys, if you can like break this one, and that was okay, I have to do it. And he was like thinking how we can break this cipher. This cipher was like considered unbreakable. And Charles Babbage breaks it. So what happens is, how does Babbage breaks it? So what he notices is, if you receive a large amount of ciphertext, for example, Kevin receives large amount of ciphertext. On the way there was Anna was trying to send Oscar, and Kevin is trying to like see what does it mean. So let's see what happens. For example, what Kevin can do is, let's say the size of the key is 6 characters. So we'll do this K0, K1, K2, K3, 4. Okay. And TH. Let's say Anna is trying to cipher this text using the key, this key. So what happens if she at first cipher this character with this key character, right? And it becomes like cipher 0, cipher 1, cipher 2, cipher 3, cipher 4. These are all one character. Now she's like out of her key characters, right? And D comes here. So what would be like? Key would be what? C0, right? C0, and H would be what? C1. C1, and U would be what? Oh, sorry. C1. Sorry. C1 and C2. Okay. Now, you see? And now Kevin notices that, okay, so I see something that is repeated. So Babbage noticed that if you find this repeated pattern, you can like guess the size of the key. So if you see the pattern like this, what would your guess? What would be the size of the key? 6, right? So once you guess the size of the key, this is what Babbage did. So he knows that this guy over here is encrypted with this key, right? This guy over here is encrypted with this key. And then K3, K4, K5, K0. This guy over here is also encrypted with the same key. Now, what he did, took out all these things, like these things, and did the same way that he would break the Caesar cipher. You know why? Is it like understandable what I'm saying? Because this thing was encrypted with K0, right? This thing was encrypted with K0. Whatever you see here is encrypted in K0. So all these K0 stuffs are equivalent to Caesar cipher because it's only single character that you're ciphering. You would like take all this thing, make a frequency analysis, break it for K0. We'll know that what is in K0. And you do the same for K1, K2, and K3 and K4. Okay? So if you're using the Wigner cipher and your key size is small, you're vulnerable. No longer you can assure that no one can break your cipher because if you apply the Babbage's method, it will be broken. Once Babbage notices this thing, he couldn't publish that, okay, now I know how to break the unbreakable cipher. Why? Because the government says, hey, don't do it. Because we're like we're sending messages to other people using this cipher. Now if you tell this thing, our enemies will know. So nobody knows that Babbage is like for a couple of centuries. Yeah, he was not recognized for breaking this key. So the government pushes him, and he didn't never publish it. Okay, so that cipher was eventually broken. Now, like code makers was like breakers like, yeah, we are victorious. Now what happens is the code makers, they keep trying to make better ciphers. So like maybe in 1970, like 30 years ago, in the United States, some guy in the NSA, he came up with a cipher that is based on the Wigner cipher, but it is considered unbreakable, and it is like used for really classified communication. So how does it work? So what is the weakness of Wigner cipher? If this key is small, you're vulnerable, right? So the larger the key is, the harder for it to break, right? So one time per cipher, it makes like, for example, you want to send something to Russia, and so characters are 50. For one time per cipher, the key would be like 50. Huge, like big key. And this cipher is actually used to secure the red line between the United States president and Russian president's red telephone, something like that. So each time they want to make a communication, they look through the time pad, and whatever there's like maybe 1,000 or 2,000 size key randomly generated, they will use that one and make the communication. After the communication is done, they'll just scrap that key away and the new one will be used. Okay? So this one is like considered one of the unbreakable ciphers. But the problem with these ciphers is like, for example, Anna wants to communicate with Oscar with this one time per cipher. So at first she has to let him know that these are the keys, right? The big pieces of keys, and somehow if Kevin like intercept that and make a copy out of that, then like useless. The communication will be transparent. Okay, so that's the problem. And then okay, so during the during the Second World War, Germans started using one type of cryptography. They call it Enigma, and it is like one of the times that human beings started using the mechanization of the cryptography. Previously, that you have some keys and you write down this thing, that thing. Now you have to, like, you're in war, you have to be fast, right? And they start using the machines that let them do it. So this is how an Enigma machine looks like. How many of you have seen the imitation game? Okay. So that was the thing that I was pretty much trying to break, because Germans was like making communication with Enigma machines, and it was important for their enemies to understand what they are going to do now, why they are going to attack. So yeah, they were trying very hard to come up with something that can break them. So Enigma machine has, like, you see, these are the keys, and this is like the Enigma opened up. It has some, these are called scramblers. So what happens is, once you press a key, these things rotate. Each time you press the key, these get rotate. Okay? So you can use only 26 characters, that is like regular English, and no spaces, no semicolons, whatever. I press the key, this guy will rotate once, and once this guy rotated 26 times, this guy will rotate once. This guy rotates 26 times, this guy will rotate once. It's like the hour, minute, seconds thing, right? The seconds rotates every time, then minute, after 60 times the second goes, then hour, after maybe 12 times, like that. So if you press this guy over here, the ciphertext for this character will lit up here. There's some bulbs that will, like, start glowing, and you know that. Or I press character A, and its ciphertext is like maybe U, E, whatever. So we're gonna be like going a little bit deep into what's going on this side. Okay. So this is a diagram of the Enigma. So Enigma, as I said, it has 3 scramblers. This guy rotates. There is a reason that why it rotates. I'm going to tell you. This one is called reflector, and this is the keyboard, and this is the light board that we saw. If you press T, there will be a connection between from here to here, and it will go the red line from there, and it will go. This is the electrical circuit. These things has wires inside them. So basically, once you press this, from here electricity will go there. There is a reflector part that sends it back. So it comes there, and then it comes here, and G is lit up. So for T, the ciphertext would be G.
So it essentially checks every turn. Like all those up there is checking which letter it's at, and it's like, all right, what's that letter? And we're gonna use it.
It basically makes an electrical circuit. Yeah. And once you release the key, this guy will rotate, and the connection will be changed. So next time if you press T, it is not going to be the same G again. It can be something else. Okay? So after 26 times it rotates, this guy rotates again once. So it makes sure that like it is equivalent to the beginner cipher we just saw a little bit ago, but it's like the key size is very, very big. Okay. Now the good thing about Enigma is it's very quick to cipher and decipher. For example, if you know the setting of the Enigma, oh, by the way, the key of the Enigma is the setting. This is scrambler, let's say 1, scrambler 2, scrambler 3, and there are some like connections. You can like connect T with T, or if you want, you can like connect T with any of the 26 you want to. So the setting of Enigma is the key of Enigma. If you know the setting, if you press T, G will go up. And now, for example, if you reset everything, if you press G, T will lit up. Okay. So you have the setting. You like make the encryption. You send it to your friend, and then they make the same setting, and they just type in the encrypted things, and the decrypted thing comes out. So that was like really fast. Like to make it fast, it was designed that way. By the way, like is it like understandable how Enigma works? It's basically, so the scramblers, if I draw here, let's say, so let's say A was here, B, C, and these are the connections. And here is your live board. You have A, B, C. Okay. So you press A, goes here and comes here, and B is lit up. As soon as you release the key, it's going to rotate. So if it rotates, now what are you doing? So what happens is these guys come here now, and this new connection will be like this. If it rotates one, new connection will be this one, and it will probably be like C. First time it was like B, then it will be C. Now one thing to notice, the important thing about Enigma, that T cannot never represent T. The T cannot be ciphered as T. There was like Enigmas, like the way it is made, it is not possible. A, if I press A, it will glow. That is not going to happen. Okay. So how hard it is to break the Enigma? Now each scrambler, you see here, it is like it has 26 characters, each one of them. So you can start like put like such way that A is on top. You can like make B is on top. Rotate one, C is on top. So C is on top. So for each one, you can like make 26 combinations, right? So only from scramblers you have like 26 combinations. Then from here you can connect this A to any of the 26, right? So from Blackboard it comes like factorial 26, which is a huge number. And you can like make this one here, like make arrangement between the scramblers, that is factorial 3. So in total the possible number of settings or keys are this. Wow. If Kevin wants to break, like, know what Anna is trying to say to Oscar, using Enigma, he has to like go through all these possible settings and check. Good luck with that, Kevin. So these are the advantages of the Enigma, that you can like quickly cipher and decipher, and these are like the settings and whatever. And Alan Turing actually made every advantage of Enigma into its disadvantage. Okay, so I wouldn't go like very deep inside. So what Alan Turing found is the huge possibility that of number of settings comes actually from the factorial 26 part, the Blackboard part. But if he can somehow figure out like the orientation of this scrambler part here, which is like 26 multiplied by 26, like 17,000 something, then he can possibly break the whole thing. So that's what he did. So what he did is, the idea is something like this. So every day morning, Germans would like send some weather report to its soldiers. Hey, today weather looks like this, cloud is this and that, and humidity is this, Alan Turing mode is that. And they're sending like weather part. So what he did is he made a like a brute force search. That this one is like several many enigmas that keeps working and working and working. And he looks for like the word weather. Is there in the text anything weather for this setting? And if some of the settings it tells okay, for this setting I have like something that looks like weather, then you just quickly set an enigma to that setting and decipher all things. Like it's a bit complicated. I wouldn't like go inside that much, but Alan Turing like come up with the thing that was like advantages of the enigma. He made it like use against enigma. And also there is a, you know what is pruning, right? Pruning means like I don't have to check these possibilities. I know right away. Now enigma has a problem that A cannot be ciphered as A, right? Alan Turing also like noticed that if like I'm trying to check this possibility and it appears like that A is gonna be A, no, don't go that way. Check something else. Okay. So that was enigma, and if you see the imitation game, you'll see that Alan Turing is trying to come up with something and come up with some machines and stuff like that. So looking for some set of words and also like pruning lots of possibilities was one of the keys that like you can quickly search through the whole search space and break the code. Now, so far, what we saw is the private key cryptography. Okay, I'll be done in 10 minutes. You guys are bored. So, what happens with the private key cryptography is at some point, Anna has to meet Oscar and tell that this is the settings, right? So that's what the Germans did. For example, to make their enigma operators to work. For example, they have like their enigmas inside their submarines and stuff. They're like huge books of settings or keys that would be like used for months. They have to give it to them by their source. But what happens, for example, Kevin captures one of the setting books from Oscar. Now everything that Anna tries to send, Kevin will just look through the book. Okay, this is setting. All right, I know. Okay. So that's a really hard problem for the whole civilization. If I want to send something securely, I gotta be meets at some point, or somehow I need to send private piece of information securely to my intended person. And if that doesn't happen, like many of the times Germans, their ships were captured and their code books was revealed, and like the allies, they're like, okay, now we know what they said. so that was like really hard problem. So there's never any method that is like, okay, so Anna doesn't have to like meet Oscar, and doesn't have to like share that private information, and still she can like transfer some piece of information to him. That didn't happen in the history. So what happens is like, what happens in 30 or 40 years ago, one gentleman, this D.P. Whitfield, he was obsessed with the problem that, okay, in the history, nobody did it. If I can do it, I'm gonna be in history. Okay? So he was like thinking like, is there any way, like, I don't have to meet, like Anna and Oscar doesn't have to meet together or somehow send the private information together, but yet they can send the information and they can be sure that nobody can read or whatever I'm trying to say to him. And he was like desperately trying many things. So what happened is he graduated from MIT, by the way, and he was obsessed with this problem. And then he found nobody believed him. Like everybody thought that it's impossible. That was never done in history. And he met a professor in Stanford, and they talk, and then the professor said, okay, you just come into like Stanford, be a grad student, and like you'll be making something. And at that time, like government was like the government was not like didn't like very much the part that one person is sending some message to another person, and the key is not shared. Government like enforced some rules that if Anna sends something to Oscar, their powerful computer will be able to break it by checking the many possibilities of the keys and stuff like that. Diffie didn't like it. So for 2 years he struggles, like come up with something, come up with something. Here he says, like the professor, Martin Hellman, who also worked with Diffie, they said that to be like good in life, you have to be fool. Why? Because first time the fool thinks that, okay, I'm going for the idea number 1, then it fails. Idea number 2, it fails. Idea number 3, it fails. Only fool will go to idea number 100, and even if it fails, he will keep going. Okay? And at some point, like when all the possibilities are like diminished, then you meet the possibility that like, okay, now it works. Okay, so, but he says that, okay, you have to be fool. Like you, no matter how many times you fail, it doesn't matter. And he says, God rewards the fool. And I would like to say like some interesting story of Diffie. So what happened is he was like so frustrated, he couldn't come up with something that, okay, somehow like can we do something that like the private key is not necessary or something. At one point, he told to his wife, look, I'm not a worthy person. I'm stupid. Like, divorce me, you deserve someone there. And his wife said, it's okay, like, I love you. But yeah, eventually, they discovered the public key. So what's the idea of the public key? Let's take a look quickly. So this is like, let's do an analogy. So let's say that I have a piece of paper. Okay. I have a piece of paper, right? Okay. And I have a color, and I write something with that color, and it's invisible. And I send it to you, and only if you have the same color that I had over there, and if you put it on the paper, it is visible. Otherwise, it is not. Okay? If you tried red, it wouldn't work. Blue, whatever. You just need exactly the same colors. So what Diffie proposed is he actually came up with like 3 names. Alice is trying to send something to Bob, and in the meantime, some evil guy, for example me, her name is Eve. She's trying to intercept the message and try to understand what is inside the message. At the beginning, Alice and Bob says to the whole world that we're going to be using yellow color. So everybody knows it's yellow color. Then what Alice do is 1 liter of yellow color, he puts 1 liter of his secret color that only he knows. Okay? This is the mixture. This is her secret color. Bob does the same. Because everybody knows the yellow, he puts inside this color? Turquoise. Okay, turquoise. He makes this color. And he sends it to Alice. Alice sends it to Bob. Okay? Now, what Alice does is, this thing was received from Bob, right? Now Alice puts her secret color into this, he gets this color. And Bob does the same, and they ended up with the same color. Okay? So now, if he was thinking of how 2 computers can communicate securely. So sending something to one computer to another computer is trivial when you have internet, right? Now they have the same color. Now with this color, Alice is going to write something and send it to Bob. And what is going to Bob do? Apply the same color on the page. He's going to be able to read. It's amazing. It's very wonderful. Now the catch is this. Everybody knows yellow with the first color, right? It's called the public key. And it's called one-way function. Once you add some other color inside, even if you know that yellow was the first color, you shouldn't be able to know what other color was added. Okay? This is called one-way function. You cannot do it. So let's do an example. See an example. How does it work in mathematics? So to do this thing, Bob and Alice, they come up with they publicly say that, okay, we're going to be using 2 numbers, 23 and 11. Okay? And Alice picks a number, secret number that only she knows, 6. Then what she does is he makes this g to the power a mod t. So g is G is 11, and P is 23, and A is her secret number. And doing this simple math, it figures 9. Okay. Now she sends this 9 to Bob, and Bob does the same thing. Bob sends his result to Alice, and then once Alice got Bob's result, he does another mathematical function. Now she has like 8, and Bob also got the same 8. Okay. And even if in the meantime, for example, when Alice is trying to send 9 to Bob, I capture the 9. Even if I know G equals 11 and P equals 23, I cannot know what is the secret number of Alice, because mod is like one directional function. So 10 mod 3 is how much? 1. 1000 mod 3 is 1 still. So if I know the number 3, and if you know the result 1, I don't know necessarily what was the number, right? And now they have the same key. Using the same key, they encrypt the message, sends it, and Bob is able to like understand what they are trying to say. Okay, isn't it amazing? Yeah. It took them like, they're so frustrated to come up with this thing. 2 years and after years, and they come. And now this tiny little problem with this. Alice always have to stay awake in front of her computer, because anytime Bob can be sending a message and she might miss it, right? So it has to be exchanged. I give something to Oscar, gives something to Anna. Anna replies to Oscar right away. If Oscar doesn't receive that thing, there will be no communication, right? Anna cannot sleep. Anna has to wake up all the time. That was a problem, and that was actually a big problem. So that problem was solved by 3 gentlemen. I forget their name, but their name starts with one like R, another one's name starts with S, another one's name starts with A. So they come up with something like that is called RSA. RSA, the idea is something like this. For example, Anna wants to send some text to Oscar. What she does, she creates a key like this, and she designs box like this, or what do you call this? Chest? Chest. It can only be opened with this key, okay? And the thing is, if anybody gets this box or chest, they cannot reverse engineer it. Like they cannot like make a key that will open it. What Anna does is he like gives everybody, hey, take this box, take this box. She gives everybody one of the boxes, right? Oscar has one of the boxes of Anna. Then Oscar, what he does, he puts the information that he wants to send to Anna into one of the boxes, locks it. Once it is locked, even Oscar cannot open it. Oh, right? I see. Now, Oscar sends it to Anna, and Anna has only the key that she can open, right? Now, Anna can open it. So this is called like another example of public key. The first example, the Diffie-Hellman, the public key was remember the color, right? The color, everybody knows that yellow color would be the thing. In this case, these boxes are called public key. So Anna makes the key and then gives everybody this box, hey, take it, take it, take it. And just anybody just takes Anna's public key or this box, send their message, sends to Anna. And whenever like Anna probably is asleep, but whenever she wakes up, he logs into her computer, and she says that, okay, there is a box coming. Using her key, she opens it. Now, how does this thing work in mathematics? Okay, there's a very simple example. So what Anna has to do is she has to come up with some numbers. So let's say she chooses like P equals 17, Q equals 11, and E equals 7. Now, he computes N. He multiplies P by Q, P, and she got 187, right? And using these numbers, she calculates her private key. So private key is something like that. So P minus 1, Q minus 1. And you come, her private key is D. D is a number such that if you multiply D by E, then you mod by P minus U, multiplied by Q minus U, the mod should be 1. Okay? So if you solve this equation, you get 23. At 23 multiplied by 7. If you mod that by these values, you're going to get 1. Okay? Now she's ready to communicate with the world. So her public key is these two pair of numbers, E and N. E is 7 and N is 187 that he makes public, like the chests. And her public key is 23 that she keeps secret. Okay? Now if anybody wants to send her a message, for example, Bob wants to send Anna a message. Let's say X, and X is in some emoji, I don't know. And its ASCII value is 88 in decimal. What Bob does is the encryption is M, the message is X, right? And its value is 88. M to the power E mod N. So from where did he get these numbers? E and N?
E is the number
Of Anna, right? Anna published it. So 88 to the power 7 mod 187. He gets 11. Now even for Bob, it's impossible from 11. He cannot come back to 88. So after sending the message, if he forgot what he sent, he doesn't know anything. Okay. Now that goes to Alice's mailbox. Alice's mailbox has 11. Now Alice wants to see what was inside the box. So using her public key, private key that only she knows, this crypto ciphertext was 11. So 11 to the power D mod N. 11 to the power 23 mod 187 is 88. Exactly the same. There's only one character, but if you take longer characters, it's still like the numbers, right? You just do the same thing, and only she can open. Okay. So now this one is very heavily used. This is for the RSA cipher. Everywhere it is used. So you're making a transaction in, for example, using your credit cards. Your credit cards information actually was encrypted with these things. It goes in the meantime. Nobody can understand what is inside it. Only for example, Amazon, only they know because they have the deed, the public key. Okay. So now you may ask this question, how hard it will be to from 187, is it possible to come up with P and Q? If you know the P and Q, you can come up with D very easily, right? Yeah. So can you factorize 187 into two prime numbers? If you can break it. Now RSA guys does this, they have huge numbers. Huge numbers. Even if all the computers tries for millions of years, they cannot come up with P and Q. So yeah, it's not breakable. So okay. So now RSA can be broken too. So for example, the factorization, from that number you're trying to come up with P and Q. That's a very hard problem for the computers that we use, the sequential computers, because it cannot check billion combinations. You have to go 1 billion possibilities. But the quantum computers, what they can do is they can check all the 1 billion combinations in one, in the singular time. So they can just break the RSA right away. But fortunately, the quantum computers are still not there. So RSA and our information that we send to Amazon is still secure. As soon as it is available, it will not be secure anymore. And so they will be breaking every the ciphertext and everything. Now the code makers, they're on the point of losing the game. They come up with another cipher using the quantum mechanics, and that one is unbreakable. So that's a little bit each topic. So yes, that was what I wanted to say. Thank you very much for coming.